Welcome. So in this video, we are going to be starting our look at kinematics, which AP calls representations of motion. This is going to be the first video within kinematics, so we're going to start off with the basics here. That's going to be focusing on how we can represent or describe the motion. So AP wants you to be able to describe the position, velocity, and acceleration of an object using various representations of that object's motion. So I listed a bunch below that are going to be common in Unit 1. So for example, diagrams are going to be something we should be able to create, interpret, and to take and transfer to one of these other ones, such as text and narratives. With text and narratives, again, we can be given these or asked to create our own, but these are going to be claims that we can make about the motion, justifications we can make for those claims, again, using words, or these are going to be like descriptions via text. We should be able to graph these, and the two types of graphs that we talk about are qualitative graphs, just showing the graph's qualities. These are like sketches, the shape of the graph, no numbers. And then there's, of course, graphs that do have numbers and they have the quantities on them, and those are called quantitative graphs. In particular with graphs, we want to be looking at the concepts of the slope of a graph at some point or over some interval, and the area underneath. That would be the area between the curve or the trend line and the x-axis. When we get into calculus, then instead of graphs, we'll be using the functions that are given describing the shape of the graph if we had had a graph. And we'll be doing derivatives and integrals, which are antiderivatives. This calculus will be for another time. We're also going to be looking at what equations are involved, and we can make note of the fact that when an object's in free fall, then we know the acceleration automatically is going to be 9.8, and of course College Board allows us to round that to 10 at all times. So when I go through these, I want to make sure you understand that when we look at each of the types of motion that we're using examples here, I'm not trying to get you to memorize these connections. I want you to be able to understand how to make these connections yourself from scratch. So please don't try to just memorize these. It will not allow you to be successful on questions. Okay, so instead what we're going to try and do is treat each of these representations I'm showing you almost like it's a different language, like we're converting from English to Spanish to French to German, etc. In each of those, say that basically the same thing, but they do so in a different way. And we can take advantage of the pros and cons of different limitations then by choosing which is going to be most effective for a problem, or if AP asks you to draw a diagram or sketch a graph, etc. So let's start right in here. So diagrams, narratives, graphs, and equations are what we're going to be looking at. This is a follow-up to the representations that AP will expect you to know throughout the year that we mentioned here. And from a previous video, what I mentioned as being common representations in Unit 1. So you can go back to the previous video for a more general overview and for anything on vectors. So the first motion that we're going to do, I'm going to zoom in here, is going to be basic speeding up. If you look at the narrative here that I gave you, we're doing gaining speed, speeding up. It's going to be in the forward direction. So that means arrows that are to the right are going to be considered to be positive values for their vector or direction. And you can see here that I've labeled out these different variables that we have in their arrow or vector format here, so I can see their direction. So I'm going to start off on the left here, which is our initial point where this object is located. X naught is 0 meters. It's got 0 velocity. And then at the very end of our time, it's going to be to the right here at some position x. So the change in position from x naught to x we call delta x. And we, of course, at the end have an arrow here to the right, and that's going to be then this velocity v. And we say over the entire motion we have a constant acceleration a, and its arrow is also to the right. So we're representing these vectors as labeled arrows. And of course, if there were numbers, we could put a equals and whatever number that is. Let's say 5 or 20 or whatever it may be. Motion maps are going to show a dot at the center of the object at different 1 second time interval. So this dot here on the far left would be where the center of the object is at time 0. And then this dot would represent where it is as a snapshot at time equals 1, and then time equals 2, and 3, and 4, etc. So you can see here the spacing between each second, as it increases seconds, is going to increase, meaning that it's increasing distance that it travels each second. And that's one of the powers of a motion map, is it shows that. As we switch over to a graph, it's going to be important to understand how these things connect. That is the basis for all relationships that we have, is what do they have in common? So you can see here, let's start with a position time graph. I'm going to go ahead and plot these. Initial and final points, so at some point x later, some time t. And so it's traveling from x naught up to x. So that's going to be a positive delta x. And we know as this gets faster, the shape of the line is going to get steeper, and it's going to be a quadratic. What's important to note here is then as we go to a velocity time, I'm going to look at a little window around x naught and look at what is the slope in that tiny window. And you can see here that the slope here is going to be 0. So at the very end, when I make a window around this, the slope through that tiny part would be positive. So here we have a positive v through the steepness inside that dotted box. We know that the slope of a position time graph is velocity, and so that allows us to get to the velocity times. That's how they're connected. So put simply, the slope of a position time graph gives us the velocity, which is the y-axis of a velocity time graph. So for example, I know v naught is 0. I also know that from the graph over here. I'm sorry, from the diagram. So I can go ahead and plot this on the y-axis, v naught equals 0. And then our positive v at some later time. And that's going to be a straight line. I know it's a straight line because slope of a velocity time graph is acceleration. And so that means we're going to have a positive slope that represents a positive constant acceleration over this whole time. That means I can plot then that positive acceleration value as a constant over the entire time. So you can see here that they are saying the same thing, albeit in different ways. I'm going to keep going through these diagrams and graphs, and then we'll come to the equations here in a moment. So now on this one, you can see here that this is going to be gaining speed and speeding up, just like the previous one, but we're going to change the direction to backwards. So we're going to then say that we're going to have it traveling to the left, left being the negative direction. You can see here, if we start again at x naught, we'll start at x naught equals 0 here on the right. We're going to have it move towards the negative or left direction, ending at some negative x. That means our overall change in position, delta x, to the left will be negative. If I plot that on this graph, then x naught again is going to be at 0. And then we're going to end up at negative x, which will be at some later time. So we'll plot that. And that's going to also be a quadratic. We're always going to have quadratics if it's constant acceleration on a position time graph. And so this is getting faster, so it should be getting steeper. So it's going to start flat and get steeper. And again, delta x is going to be then traveling in the negative direction, which on our graph is down the position axis. If we make a little window around our initial spot, again, it's going to be flat. So that means that I can tell that v naught is 0, which is again true in the diagram. And I can plot that then as a 0 value on the y-axis. At the end, if I make a window around the ending point, it has a negative slope, which means it has a negative v, negative velocity. And so that negative v at a later time would be a point plotted down there. That will be a straight line because this is constant acceleration. And the slope, which is negative, represents a negative acceleration. And again, we can plot that as a constant over the entire time. You can see in the motion map, if we start on the right side and move towards the left, then the spacing in between each 1 second dot would increase as it gains speed. So now we're going to look, instead of speeding up, we're going to look at slowing down. So we're going to slow down, but still travel in the forward direction. So we're going to move to the right. So we're going to move from left to right. Now, if you notice here, I've already drawn this out for us. And you can see that its x naught is 0. And it's going to end up at a positive x. Again, showing that delta x is traveling the positive direction up the position axis in the positive way. And then later it's going to be at this position x at a different time. Now, it's losing speed, so it is going to be starting off already moving and then stopping. So we're going to be slowing down or getting less steep over time. So this parabola is going to have to start sloped and eventually flatten out. And that's going to end up being the vertex. Okay, now the vertex is going to be the point at which the slope is 0, which means it is stopped. So sticking with what we were doing before, we're going to make a window around this and show that it was moving forward, positive v naught, by looking at slope, and then like we started to do at the top, ending with 0 velocity. And again, this corresponds to what we see in the diagram. So we're going to now start with a positive y-intercept. This is going to be a positive v naught, and end then with a y-axis value or velocity value of 0. Since this slope is negative, that means our acceleration is negative over the entire time. And lastly, we're going to look at now slowing down, but moving the backward direction. And you can see here in both of these, if you take a look at this motion map, whereas in the previous one, we start off with a lot of spacing for the first second, and then that spacing as we travel in 1 second intervals from there shrinks, right? It's decreasing distance each second. We notice that as well here because we're going to start at the right side and move to the left, moving backwards. You can see there's a lot of spacing as it moves quickly in the beginning, and then that spacing will shrink as it approaches a 0 velocity. So let's go back to our graph. We're going to start off x naught here. We don't have to start at x naught of 0, but we can choose our tape measure often to just be at 0. So it's just a convenient thing to do. Most times we're just concerned with delta x anyway. We don't really have to use x naught and x as separate values. We just want to know what the change in x is, or delta x. So x naught of 0, and then x is going to end up some negative value at some later time t. And this is going to be getting less steep. So it's going to be a parabola that's going to be getting less steep. And so we're going to start off sloped and flatten out. Again, if it's truly at 0 speed, then this point here would be the vertex. If we make a window around the beginning point, we see that it has a slope that's negative. So that means we should have a negative v naught by looking at slope. If we make a window around here, then we're going to assume that that's flat, which would mean the ending speed is 0. Again, looking at slope inside our little dotted window. That means we have to plot a negative velocity initially, or y-intercept that's negative. And then since this is stopping, it will be a y-axis value of 0. That will be a straight line because slope is acceleration. This is a positive slope, therefore positive acceleration. It might be important then to check to make sure everything matches, right? We have to be able to not only interpret a diagram, interpret any of these three graphs, interpret these narratives and motion maps, but we should be able to translate from one to the other. So if I give you any one of these, you should be able to produce the missing ones for that same motion. So you can notice here, positive acceleration is a positive acceleration on these graphs and on the slope. And this, just so you know, is a very important, often misused or confused item here. And that would be that most students, when they come into introductory physics, they think that negative acceleration means slowing down, and that is definitely not the case. So do not let that be something that confuses you, right? And this is an example of that. Slowing down can have an acceleration of positive or negative. And this last one here is an example of a positive acceleration for slowing down. Likewise for speeding up. Speeding up can have a negative acceleration or a positive acceleration. Really what matters is the acceleration working with the velocity, speeding up, working with the velocity, speeding up, or is the acceleration working against the velocity, slowing it down, or against the velocity, slowing it down. So the diagram is a very good way to depict speeding up and slowing down by looking at the velocity and acceleration arrows. Let's jump over to the equations now. And as we go into the equations here, I do want to point out that there is a daily video that would be good for this graphing concept here. So if you wanted more help with the graphing, you can go to daily video 1 for this 1.3 unit, and that should be some additional information there that may help you. And now we're going to be looking at the equations. And so if I look at the equation sheet that we have for mechanics for AP, you notice in the top corner here, these three equations. And those are really the equations that we're going to be using for constant acceleration. And those I've kind of copied over to be right here. So assuming that we have a constant acceleration, because that's what we had in all of these situations we drew here, that includes not only gaining or losing speed, but also constant speed. And constant speed would have 0 acceleration. So it would be not a positive or negative, but 0 acceleration. Then we can use those three kinematic equations that I showed right here right from the College Board equation sheet. Now you notice here there's like a little x subscript for these, and that's there to show you that it has to act along an x-axis. And there's also then this x minus x naught, and that's really just delta x. So since we know we can only apply these along a single axis and for a constant acceleration, and that delta x is x minus x naught, then we can write them like this. Notice here I've just dropped off that x subscript and I've replaced the x minus x naught with delta x. So these may look more familiar to you because this is how we use them in freshman year. We also had a fourth one freshman year that we can derive, and we'll be asked to derive many times. And there's also this one here that we could be asked to derive. Again, we don't have to necessarily know these. We should be able to derive them. But you notice that why do we have so many? We have 5 different variables: delta x, v naught, t, a, and v. So that means we have 5 different equations that have a combination of those variables. So each one of these equations has 4 of the 5 variables. So that means we have 5 different equations based of 4 variables. This one, for example, does not have v in it. This one doesn't have delta x. This one does not have time. This one does not have acceleration, and this one does not have v naught. So which equation we use is simply based on which equations we have provided, which variables we have provided to us in the problem. Do I know A? Do I know V? Do I know time, etc.? And what am I trying to solve for? So if I don't, for example, know v, and I'm not asked to solve for v, then this would be a very appropriate equation to use because it doesn't have that variable v in it. And likewise with the rest of them. For problem solving, we're going to be looking at that in a future video. Thank you for your time. Take care.